Are you ready? So now let us start with the IC fabrication 1 part 2. So in the previous one we stopped at the soft bake. So now we are going to continue with the next step for the SI wafer preparation, which is photolithography. After the process of soft bake, where we finish the cover of the SI wafer with the silicon oxide and also the photoresist. Now the process of printing will take place. So this is what we call as photolithography, which is the process we want to transfer the geometric pattern on the mask so that to the surface of the prepared SI wafer, so that we are going to get the circuit design that we want. So usually UV light is used to transfer the pattern from a photomask to a light sensitive chemical photoresist. So the most common one that we use is UV exposure. Okay, so there are other processes also you're going to look into later, like for example X-ray lithography, ion beam lithography. So that one we go after this. So what I want you to understand is the process of transferring the geometric pattern to the mask first. Okay, so usually UV exposure will be placed on the mask that we already designed, and then there will be a development process where we want to develop the circuit on the what we call the SI wafer, and then the wafer will go through hard baking process. Okay, so let's see the process. Okay, in order for us to do the UV light exposure and to perform the printing of the circuit on the SI wafer, we do have to align the mask to the SI wafer. Okay, so mask alignment is very crucial step, if because we are the process involve a very small area for printing. So the mask, if a slight tilted area also will highly influence the properties of the circuit that we are going to print on the SI wafer. So that's why mask must be properly aligned with the wafer so that the pattern is accurately transferred to the wafer surface. There are three main methods for the UV exposure to the pattern. So they have contact, proximity, and also projection. Okay, so we will look one by one on this one. Okay, so for contact and proximity, usually it is a lab scale or individual MEMS devices. This one is not used in the industrial because of why we look into this process. And then the projection usually used in the industrial scenario, for example, the IC, microchip, VLSI printing. Okay. So the first one is contact printing. So since the name is contact printing, meaning that in the process of printing the circuit, the resist coated silicon wafer will be brought in physical contact with the mask. Okay, so for example, if you can look into this picture, this is the wafer, this is photoresist. The mask is placed directly on the top of the photoresist. Okay, so it's in contact with the photomask, and then before the UV light is exposed on the mask, then it will print on the photoresist. Okay, so the wafer is held on a fixture via vacuum, and then the whole assemble is raised until the wafer and mask contact each other. Okay, so it will be contacting to each other. The resolution will go up to 2 to 3 micron features, and the mask must be in 1 to 1, meaning the size of the mask and the wafer must be equal. Okay, so then uh, the problem with this one is there is a possibility for debris that will be trapped between the resist and also the mask. Okay, so there might be a debris on this layer in between the mask and also the photoresist. So this one will damage the mask, and also it can also create a defect to the pattern that we want to print on the photoresist here. The second one will be proximity printing. So as the name, it is proximity printing, meaning that uh, it is not in contact with the photomask, but it has some gap around 5 to 20 micrometer in between the mask and also the photoresist. Okay, so this one similar to the contact printing, except they have small gap that maintain throughout the process. This gap will minimize the mask damage. The resolution again is around 2 to 3 micron resolution, and the mask also need to be 1 to 1 in ratio, meaning the same printing size must follow with the to the size of the wafer that you want to print. Okay. However, this proximity method does not entirely eliminate mass and wafer damage. So why? Why it is still not good enough compared to the contact printing? So the problem is it calls the near field Fresnel diffraction effect. So what is this near field or Fresnel diffraction effect? This is due to the light diffraction. So instead, because of the mass, what we call the mass is lifted from the photoresist, there is a gap in between here. So what happened is there will be a certain diffraction of light to the side, like this one, like the one that shown in the arrow here. Okay, so this can be calculated by using this equation. So that mask aperture, this is the mask aperture, so this is the area where we want to expose to the UV light. Okay, so you will see that there will be certain measurement that you have to calculate for this diffraction. Okay, the last one is the projection printing. So projection printing, they are using the condenser lens. So for example here, the light, UV light is exposed to the condenser lens. It goes to the mask, and then it will be projected on the projection lens before it goes to the wafer. Okay, so this one uh, they are placed many centimeters away from the wafer here. Okay, so projection printing avoid mask damage entirely, and then the resolution can goes up to 1 micrometer resolution, and the mask to wafer ratio is around 1 to 1 also. In the projection printing, there is one things also that we have to take what we call attention, which is far field for Fraunhofer diffraction effect. This one you have to calculate properly in order to get a good printing. So if we in the light, if you see into this area, so this area here where the light is focused, there are still have some light that what we call reflected on this area. Okay, so that's why we have to do some calculation in order to get the light length, how it's exposed on this one. Okay, so it is calculated by using 1.22 f what do you call this, lambda, well, lambda over 2. Okay, so this f is the focal length of the projection length. Okay, so here collective light, meaning the distance between the projection lens to the what we call the photoresist, and also the wavelength of the light also must be take into consideration. Okay, so this one is this picture showing the effect of the diffraction that previously we look into. Okay, so usually the light will be the intensity will be maximum around here. So but then there are still some intensity of the light on this area side. Okay, on the side here. So we have, in order to do the focus printing, so you have to consider the calculation of the L here. Okay, so if there we require to print even smaller size into submicron what we call printing on the photoresist, projection printing with the stepper method will be used. In this case, projector lens use selected to reduce mask pattern size transfer to wafer by 2 to 10 times, meaning that the size of the printing will be very small from the mask itself. Okay, it can be smaller by 2 to 10 times. The resolution can achieve down to 10 second of nanometer. Okay, so currently the most common method is fabricated for the VLSI IC and also the CPU chip. Okay, so how does the stepper method work? Okay, so for example, this is the projection lens. They are going to use reticles here. So what is reticle? It is like a scale, a board where it can focus where we want to print the what we call the design on the wafer. Okay, so then the light will be focusing on each box until we finish printing the what we call the design on the photoresist. Okay, so this reticle will be used first. The whole must okay, you print one pattern on one area. Okay, and then it will move to the another one, meaning it's stepper. They step from one to another. Okay, so then it will print the second one, third one, fourth one, so on the SI wafer. Okay, so this is what we call as stepper method. This stepper method is very expensive. Why? Because it's require a very what we call very precise instruments, so that there'll be no error in printing the circuit, because it's moving from one to another, right? So we don't want like it's the design is already printed and then it's overlapping on another one. Okay, so that's why we need a very good setup for this method. Okay, so it requires high precision and control, so that the position, temperature, vibration, and also what we call the printing itself in a good quality. That's why the complex and expensive system is required. So the reduction of image give high precision and small pattern. So a mask with 1.25 micrometer feature size can be reduced to 0.125 micrometer size, meaning that a big size mask can print a very small size circuit on the chip, on the SI wafer. We're going to look a little bit on the how does the UV exposure work on the photoresist. Okay, so for example, here you will see that this is UV light. Okay, and then we have the mask, and let's say the blue one is the opaque chrome plate. Okay, and then this is the photoresist silicon outside layer, and also this is the N-type SI wafer. Okay, so let's say this area is already exposed with the UV. After that, the exposed wafer will be placed in the cartridge tray, and then it will be immersed in the resist which is which developed to what we call to wash away the exposed region. So this is for the positive photoresist lah. If you use positive photoresist, then it will wash away this area that is being exposed to the UV, and then you immerse it in the second solution, so that it will further resist development. So meaning that it does not penetrate into this silicon area. After that process, we go to the hard bake process, where the wafer will be baked in the temperature of around 130 degrees Celsius to 160, in order to hydrate the photoresist prior to subsequent etch and also the ion implantation process. So this bake will stabilize the resist characteristic, then make the resist less sensitive to this hostile process, which is the etch and also the ion implantation. So this one we will be covered in the next class later. Okay, so then the H2O will go out from this photoresist. So we stop our lecture today by with that process first, so that you have the time to digest all the information. I think that's quite a lot of information that you're gathering today. So we're going to continue with the IC fabrication 2 in the class on Monday. Okay, inshallah. So if you have any problem regarding this topic, please let me know, because I know it is a new process, so it might be a little bit tricky on understanding the process. Okay, with that, thank you very much for listening. Assalamualaikum.